Hello, my name is Josh Reingold, and this is my report on the motion of a falling object for Physics 2. The purpose of this lab was to analyze the movement of a falling object using Tracker and create two different predictive algorithms that projects the movement, one only accounting for gravity and the other also accounting for drag. This lab utilizes the principle of gravity and how theoretically a falling object experiences a constant force due to gravity. However, it also explores the principle of air resistance or drag and shows that a more accurate model must account for this change to the net force, which is non-constant due to air resistance being calculated by instantaneous velocity squared multiplied by a constant v. From the data collected, I determined that the predictive model that accounts for air resistance is closer to the observed data than the model that only shows gravity. The gravitational model can be used in environments such as vacuum chambers, but since a light object was dropped in a normal room, it is more accurate to use the drag model. The system for this experiment is the paper box that I dropped, and the surroundings are the air and the room around it. The initial conditions are that the paper box had 0 initial velocity and an initial height of 2 meters above the ground. I dropped the paper box and videoed it as it fell. I imported the video into Tracker, set the axis at the center point of the box before it started falling, and then recorded the position of the box in each frame as it fell in the negative y direction. I then imported this data into an Excel document. Afterwards, I imported the starter code into a Glow script and adjusted all the necessary parameters, such as delta t, the mass of the object, and the net force, to create two different predictive algorithms. The first only accounted for gravity, and therefore the only force acting on the object was mg. The second algorithm, however, also accounted for air resistance, and used the formula mg minus bv squared. I modified the models several times to get them to predict the motion as well as possible. After running the final program, I imported the data results into the same Excel document as the tracker data. Using both the observed and predicted data, I created two line graphs displaying both sets of data of the same scale. The first graph shows the position versus time of the object in the observed, gravity predicted, and drag predicted models. This graph looks somewhat linear because the data range for this experiment is comparatively small. Because the gravitational model only accounts for gravity, it predicts the box to drop faster than what was observed. When also accounting for air resistance, it is observed that while the two models start the same, the air-resistant model quickly diverges from the gravitational one and better matches the observed data. Because the drag force is proportional to the velocity squared as the box speeds up, the model more accurately captures its motion. Some possible sources for error during this experiment was that the box might not always have maintained a perfect surface area while falling. This would have affected the b constant in the drag formula and therefore impacted the observed data. Additionally, there may have been impacts from the environment, such as a breeze or unknown airflow. I then used both models to create a velocity versus time graph. The gravitational model is linearly increasing because it exerts a constant force and therefore a constant acceleration or change in velocity. However, the drag model shows more of a radical curve because as the velocity increases, the drag force increases, and therefore the change in velocity decreases. If the data continued, this would come infinitely close to flattening out, or no longer having increasing velocity, which would show the point of terminal velocity, where the drag force cancels out the gravitational force, causing the net force to be 0, and the box is falling as fast as possible. If the object was thrown downward, there would be an increased initial velocity. This would cause the object to reach terminal velocity faster because gravity is constant, but an initial velocity causes initial drag, which would more quickly reach the point of 0 net force. In summary, this lab successfully demonstrated that a falling object experiences a drag force, and that an algorithm which only accounts for gravity is not sufficient in modeling that behavior.